Hi, people. Um, for my guys, if you're watching this, you should have already solved this problem. So hopefully you already solved this problem. And if you haven't, stop and come back when you're done. So if you're ready for this, you have all the tools before we get through what we're about to go through. You have my guys have all the tools to solve this problem, and those tools are the following. Delta x is v average times t. Anything so far that says how far did something go, that's what we're using. All right. Although this thing, we have a rate of change of velocity, and we define the rate of change of velocity to be acceleration. All right. I'll just remind us that if we want a nice average velocity for velocities that change uniformly from one value to another, we just add and divide by 2. Okay. Um, so what we're going to end up doing with these 3 equations are writing 3 more equations or developing 3 more equations that allow us just to talk about things maybe in a little different context or from a different perspective. And that perspective is going to be, how do things end up? All right, this is sort of already in that context or from that perspective. How far do I end up away from where I started and in what direction if I move with an average velocity for a certain amount of time? This one is not really written in that context, but we can write it in that context or from that perspective if we rearrange a little bit. And I'm going to start there. So I'm going to say that, all right, A delta V over T. Well, delta V can be written as V minus V naught. All right, that's how we do delta anything. Take final, subtract initial. All right, and if we want to write this from the perspective of how things end up, we're going to solve for V, because that's the speed we end up with, or the velocity we end up with. So AT, multiply both sides by T, is V minus V naught. Add V naught to both sides, and we get the following. First, what we call kinematics equation, right? And that says that the velocity you end up with depends on the velocity you started with, and it depends on if and by how fast you accelerate and for how long you change your velocity. All right, so that gives us the velocity we end up with after some acceleration. And of course, it says that if acceleration is 0, no matter how long your acceleration is 0, then your initial velocity and final velocity will be the same thing. Okay, so there's our first what we call kinematics equation. Yeah, do it. Do it. Did you do it? Do it? You didn't? Creepy. Yeah. Put that over here. Good. We'll get rid of this stuff. Now our next one, what I'm going to do is I'm going to use this and this. All right, and what I can say is that delta x v average times t, well, that means that delta x is, let's see, v average, v plus v naught over 2. And t, well, what I'm going to do for t is take this one and write an expression for t. Well, t, by definition from that one, is going to be delta v over a. So this I rearrange for t and put it in there. And that means I can write this as, well, instead of delta v, why don't I write it, nice and explicitly about how we do delta v, v minus v naught. I'm going to clean this up a little bit. I'm going to multiply both sides by 2a, and what I get is 2a delta x is v plus v naught times v minus v naught. And I'm just going to FOIL this right side. So 2a delta x first gives me v squared. Outer gives me negative v times v naught. But inner gives me positive v times v naught. Those add to nothing. And the last gives me minus v naught squared. I'm going to rearrange this and say that v squared is v naught squared plus 2a delta x. What's the next? kinematics equation. And yeah, we don't leave it necessary. We don't choose in this case to leave it as v. Instead, we leave it as v squared. I don't have a great explanation for why. You could certainly write it that v is the square root of all that stuff on the right. But this is the way that people always leave it. All right. And so this says, at what velocity do I end up? Well, it depends. Look at the green one. What velocity do I end up with? Well, it depends on the velocity I start with and how fast I accelerate and for how much time. The bottom one is neat because it says what velocity do I end up with? Well, it depends on the velocity I started with and how fast I accelerate and for what amount of distance I accelerate over. So these two equations allow us to look at the same, what velocity we end up with, but we get to come at it from two different angles of attack, for lack of a better phrase. And those angles of attack are, do I know how long I accelerated for, or do I know spatially how far I accelerated for or over? All right, but both of those equations, depending on what you know and what you don't know, can be very valuable. Okay, the last one, the third kinematics equation, really allows you to solve this problem here in one step. All right, what you would do if you were trying to solve this problem is, well, how far does something go? You'd have to start here. Delta x is v average times t, right? Well, now what you don't know, let's see, we know t, right? 4-second interval. We know starts at this speed. This is our v naught. We know a, right? But we don't know what v is, the speed that it gets to. Well, to do that, you'd have to use this. And actually, you'd have to use it in this form. V is v naught plus at. You'd have to rearrange this. Whether or not you knew this equation that we derived, you need to know what the final velocity is so you can plug it into here. Agreed? Because we know everything else. And so what I'm going to do is actually take this and substitute it in for that. Because I know you didn't do this algebraically, but as a process, what you did was calculate, hopefully, calculate what v is, and then put it in here in this equation that lets you find delta x. All right, so what we'll end up with is if we put this stuff in the brackets in there, we end up with delta x is, here's what goes in the red brackets, v naught plus at plus that first v naught that was already here, divided by 2, and then don't forget this times t. Where'd the divided by 2 come from? Just sitting right there. Okay, so now we say, let's simplify. We got a v naught plus another v naught. There's a 2 v naught plus at over 2, all that stuff times that t. I'll distribute that t through there. We get delta x is 2 v naught t plus a times t squared, right? We're taking the t and multiplying by that and by that. And then we divide by 2. And we simplify and divide both terms by 2. And we get v naught t plus 1/2 times at squared. And there, my friends, is a third equation. All right, and what's great, right, like I said, you have all the tools to solve this problem, and you had them before we came up with these new equations, but you'd have to use at least 2 equations. And now, right, we're given in this problem the initial velocity, the time, the acceleration, time, and we find out how far it went. We do it in one shot. All right, does it make these more valuable than, you can still solve any problem, any one-dimensional or really two-dimensional problem, you can still solve them with these 2 equations and knowing how you find the average of things. But what can be easier to do, or more convenient to do, I should say, is just to use one equation. All right, and so what I certainly don't need at all is I don't need you to be able to derive these equations. But what you do have to be able to do, you like that as a little mention there. But what you do have to be able to do is use them, okay, and use them correctly. And what I didn't kind of finish with is, oh yeah, I did, right? Well, how, where do I end up compared to where I started? Well, it depends on how fast you were going in the beginning, and then for what amount of time you accelerated, right? So that, again, gives us that context of how do things end up, okay? So yeah, these are what we'll call the kinematics equations. Your job is memorize them. Yes, memorize them. Okay. I will say that this is 1/2 times a times t squared, not 1/2 at squared, and not 1/2 times at squared. It is 1/2 at squared. 1/2 at squared. All right, so memorize those. We'll get some practice using them when I see you next. All right? You don't have to have them memorized by tomorrow, but it wouldn't kill you. Other thing worth noting is, why have 3 different ones? Well, notice, no delta x in here, no t in here, no v in there. So they all have something that the others don't, and they all don't have something that the others do. Okay? So, get to know them. I told you it's going to be 12 minutes. See you.